Okay, think about this. You push against a wall, right? Or just stand on the floor. Everything feels completely solid, like totally dense and unmoving.
It does, doesn't it? That feeling of solidness is really powerful.
But here's the weird thing, the really counterintuitive part about, well, everything. If you could zoom way in, beyond what we can see, how much of that stuff, that solid matter, is actually just empty space?
Ah, yeah, that's the big illusion, isn't it? It feels solid because of electromagnetic forces, the electron clouds pushing against each other, not because it's packed solid like a rock.
So you're saying most of it is empty?
The vast, vast majority. You, me, this table, the air, it's overwhelmingly void.
Right. So today, that's what we're doing, a deep dive into the atom, the basic building block. We're going to trace the story, kind of like detectives, following how scientists went from thinking atoms were tiny, solid balls to realizing they're mostly nothing, centered around this incredibly small, powerful core.
Exactly. And our mission really is to unpack the actual experiments, the evidence, particularly that game-changing gold foil experiment, the one that just shattered the old ideas.
And then connect that structure, protons, neutrons, electrons, to why the periodic table looks the way it does and why elements react in certain ways.
It all clicks together once you see the structure.
Okay, so to appreciate the revolution, we need to know what came before, the starting point. That takes us back to the early 1800s with John Dalton. What was the picture of the atom back then?
Well, Dalton really laid the groundwork for modern chemistry. His model was simple but powerful for its time. He pictured atoms as these tiny, indivisible, solid spheres, like miniature billiard balls.
Indivisible being the key word there.
Absolutely. He thought they were the fundamental, uncuttable things. He also got right that atoms of one element are identical, and they combine in simple whole number ratios to make compounds. That model held sway for, almost a century.
But then things started to crack, right? Around 1897, J.J. Thomson and cathode rays, what did he find?
He discovered the electron, this minuscule particle, incredibly light, with a negative charge. And that discovery was huge because it proved atoms weren't indivisible after all. They had smaller parts inside them.
Ah, so Dalton's solid sphere model was suddenly out the window.
Instantly obsolete, yeah. Because now you have this negative piece inside a neutral atom.
Which means there has to be some positive charge in there, too, to balance it out.
Yeah.
And that leads us to Thomson's memorable model name.
Yes. The plum pudding model sounds a bit silly now, but it was a genuine attempt to make sense of it. He imagined the atom as this big, sort of diffuse cloud of positive charge. That's the pudding.
Okay.
And then these tiny negative electrons, the plums, were just dotted throughout this positive pudding. The really crucial assumption, though, was that the positive charge and the mass were spread out evenly through the whole thing, uniformly distributed.
Right, that uniform distribution idea. That's exactly what Ernest Rutherford, along with Geiger and Marsden, decided to test around 1911. So what was the experiment? What did they shoot at this this gold foil?
They used something called alpha particles. These are relatively heavy particles, about 4 times the mass of a hydrogen atom, and they have a positive charge. And they fired them like tiny bullets at an extremely thin sheet of gold foil. Really, really thin.
And based on that plum pudding model, where everything's spread out thinly, what should have happened? What was the prediction?
The prediction was pretty clear. If the positive charge and mass are really diffuse, like Thomson suggested, then these heavy, fast alpha particles should just punch right through, like shooting cannonballs through mist.
Minimal or maybe zero deflection expected. They should all just go straight.
Exactly. So they set it up, detector screen around the foil, and started firing. And what did they see? Well, observation number 1 was mostly what they expected.
Most went straight through.
The vast majority.
Right.
Flew straight through the gold foil like it wasn't even there. No deflection at all.
Okay, that seems to fit the mostly empty idea that came later, but hang on. Even if the pudding was diffuse, shouldn't hitting some positive charge, however weak, cause a tiny bit of bending, a slight nudge sideways?
That's a great point. It should have, theoretically. But the fact that most went through with absolutely zero deflection was the first major clue for Rutherford. It led him to conclude that the atom must be overwhelmingly empty space. That diffuse pudding idea just didn't fit this straight-through data.
Okay, so the pudding model's already in trouble, just from the ones that went straight. But then came the shocker, the real aha moment.
Oh, absolutely. The part that Rutherford himself said was like firing a 15-inch artillery shell at a piece of tissue paper and having it come bouncing back at you.
That's an incredible image. What caused that?
Observation 2. A very small number, a tiny fraction of those alpha particles didn't go straight through. They were deflected at really large angles.
Not just nudged, but seriously knocked off course.
Seriously knocked off course. And even more incredibly, a few, maybe 1 in 8,000, something like that, bounced almost straight back, deflected more than 90 degrees.
Whoa. Okay, physics-wise, how does a fast, heavy, positive alpha particle get thrown backwards?
It can only happen if it runs into something that is also positively charged to repel it strongly, and something that is much more massive than itself, so it doesn't just push it aside. And critically, that something must be incredibly small, because most particles missed it entirely.
So, not a diffuse pudding, but a tiny, super dense, positively charged core.
Precisely. Which he named the nucleus.
And that's where almost all the mass is concentrated.
Yes, and the scale here is just mind-bending. You have to try and picture this.
Yeah.
If you blew an atom up to the size of, say, a huge football stadium,
Okay.
the nucleus, containing nearly all the mass, would be about the size of a single marble sitting right in the center.
A marble in a stadium.
Mm-hmm.
That's almost unbelievable. Let's just pause on that. If matter is 99.9-something% empty space, just this tiny marble nucleus in a vast stadium, why doesn't my hand go straight through this desk? Why does anything feel solid at all?
Right, it comes back to the electrons. Remember them. They're not in the nucleus. They're whizzing around in that vast empty space, defining the outer boundary of the atom.
Like shells or clouds.
Exactly, clouds of negative charge. So when the electron cloud of your hand gets close to the electron cloud of the desk, those negative charges repel each other very, very strongly, like trying to push two powerful magnets together the wrong way.
So the solidity we feel isn't actually atoms bumping into each other like solid balls. It's the electromagnetic force field between their electron clouds pushing back.
You've got it. It's an energy field effect, not physical contact in the way we usually think of it. The emptiness is real, but the forces operating within it are powerful.
Okay, so Rutherford gives us the nucleus and the empty space. But his model had a problem, didn't it? Something about classical physics.
It did. A big one. According to the physics of the time, a negatively charged electron orbiting a positive nucleus should constantly radiate energy.
Meaning it would lose energy.
And spiral inwards, faster and faster, until it crashed into the nucleus in a fraction of a second. Atoms should basically self-destruct, but obviously they don't.
So how is that fixed? Who figured that out?
That was Niels Bohr. Just a couple of years later, in 1913, he brought in early quantum ideas. He suggested that electrons couldn't just orbit anywhere. They could only exist in specific fixed energy levels or orbits, what we call shells.
Like planets in specific orbits around the sun, but only certain orbits allowed.
Kind of like that, yeah. They can jump between these allowed shells by absorbing or emitting energy, but they can't exist in between. That prevents the death spiral and keeps the atom stable. Bohr's model was a huge step towards our modern understanding of electron arrangement.
Okay, so we've got the positive nucleus, thanks to Rutherford, and electrons in specific shells, thanks to Bohr. We know the positive charge comes from protons in the nucleus, but there was still something missing, wasn't there? The masses didn't quite add up.
Exactly. Take helium. We knew it had 2 protons, that's what makes it helium, but its mass was known to be about 4 times the mass of hydrogen, which has 1 proton. Where did the extra mass come from if there were only 2 protons?
There must be something else heavy in the nucleus, but without charge.
Precisely. That was the puzzle solved by James Chadwick in 1932. He discovered the neutron. It lives in the nucleus alongside the protons, has almost the exact same mass as a proton, relative mass of 1, but crucially, it has 0 electrical charge. It's neutral.
The silent partner. It adds mass, but doesn't mess with the charge balance.
That's the one. It explained the missing mass and also the existence of isotopes, which we'll get to.
So that's our trio, proton, neutron, electron. For anyone listening, what are the absolute must-know stats for these 3? The core properties.
Okay, think relatively. Protons in the nucleus, charge +1, relative mass 1. Neutrons also in the nucleus, charge 0, neutral, relative mass 1. Electrons orbiting in shells, charge magnitude 1, relative mass basically negligible, tiny, about 1118/40th of a proton or neutron.
So nucleus, mass, protons plus neutrons. Shells is volume and chemical behavior, electrons.
And charge balance is key. Proton positive, electron negative, neutron neutral.
That's the essence of it, yes?
Now we have the parts list. How do we define what an element is? Which particle gives an atom its fundamental identity?
It's all about the protons, only the protons. The number of protons in the nucleus is called the atomic number, usually written as Z. That number uniquely identifies the element.
So 1 proton is always hydrogen, 6 protons is always carbon, 8 protons is always oxygen. Change the proton number, you change the element entirely.
Absolutely immutable. Z defines the element. And of course, in a neutral atom, the number of positive protons must be exactly balanced by the number of negative electrons. So for a neutral atom, protons equal electrons. Okay, proton number is fixed. But you mentioned Chadwick's neutron helped explain isotopes, so the neutron number can change.
It can. Isotopes are atoms of the same element, meaning they have the same number of protons, same Z, but they have different numbers of neutrons.
So same element, same chemical reactions mostly, but different masses.
Exactly. For example, most carbon atoms have 6 protons and 6 neutrons, carbon 12, but some have 6 protons and 7 neutrons, carbon 13, and a tiny amount have 6 protons and 8 neutrons, carbon 14. They're all carbon, but they weigh slightly different amounts.
And this discovery of isotopes explains something weird on the periodic table, right? The mass numbers aren't usually nice whole numbers. They're often decimals, like chlorine being 35.5.
Precisely. That decimal mass, the relative atomic mass, or artonic, is direct evidence of isotopes existing in nature. It's not the mass of one specific atom.
So what is it then, if not the mass of a single type?
It's a weighted average. It's the average mass of all the naturally occurring isotopes of that element, weighted by how abundant each isotope is. Think of it like calculating your grade point average courses with more credits, count more towards the average.
Okay, let's use that chlorine example. It's 35.5 on the table. How does that come about?
Well, chlorine mainly exists as 2 isotopes in nature. Chlorine 35 with 18 neutrons and chlorine 37 with 20 neutrons. Both have 17 protons, of course.
If they were a 50-50 mix, the average mass would be smack in the middle, 36.
Right. But the actual average, the ordinary, is $35.5.
Which is much closer to 35 than to 37.
Exactly. And that tells you immediately that the chlorine 35 isotope must be way more common in nature than chlorine 37.
So the weighting pulls the average towards the more abundant one.
Correct. It turns out chlorine 35 makes up about 75% of natural chlorine, and chlorine 37 is about 25%. If you calculate that weighted average, 35 times 0.75 plus 37 times 0.25, you get 35.5. Ah, okay. So that number on the periodic table isn't just a mass. It's actually telling you about the natural mix of isotopes for that element out there in the universe.
That's the real insight. It's a reflection of natural abundance.
All right, let's shift from the nucleus and mass back to those electrons whizzing around in their shells. You said understanding their arrangement is key to, well, all of chemistry.
It really is, because chemical reactions are all about electrons interacting, especially the outermost ones. The rules for filling these shells are pretty straightforward, especially for the first 20 elements or so.
How do they fill up?
Electrons always go into the lowest available energy level first. They fill from the inside out. So the first shell, closest to the nucleus, fills up first, then the second shell, then the third, and so on.
And there are limits to how many fit in each shell. Yes. For the simple model we use for basic chemistry, the first shell can hold a maximum of just 2 electrons. The second shell can hold a maximum of 8 electrons. And the third shell, for elements up to calcium number 20, also effectively holds 8 for bonding purposes. So it's a 2-8-8 pattern for the capacities.
Okay, 2, 8. And this structure, this filling order, it's literally mapped onto the periodic table, isn't it?
Perfectly. The table isn't just a random grid. It's organized by electron structure. Think of the period the horizontal row an element is in. The period number tells you how many electron shells are occupied in that atom.
So period 1 elements, hydrogen, helium, have electrons only in the first shell. Period 2 elements, lithium to neon, have electrons in the first and second shells. Period 3, sodium to argon, use 3 shells. Makes sense.
Exactly. It's like floors in a building. Period number of occupied floors.
And what about the vertical column? What does that tell us?
The group number is crucial for chemistry. For the main groups, like 1, 2, and 13 through 18, the group number tells you the number of electrons in the outermost shell. These are called the valence electrons.
Valence electrons. Those are the important ones for reactions.
They're everything for reactions. They're the electrons involved in bonding and forming compounds. So an element in group 1, like sodium, has 1 valence electron. An element in group 2, like magnesium, has 2 valence electrons. Group 17, the halogens, like chlorine, have 7 valence electrons. Group 18, the noble gases, have 8, or 2 for helium.
Okay, so sodium, we said, is period 3, group 1. That means 3 shells occupied, with 1 electron in the outermost one. Its electron configuration would be written 2, 8, 1.
Perfect. First shell full 2, second shell full 8, third shell has just 1.
And this all connects to why atoms react at all, right? Something about wanting to be stable, like the noble gases.
That's the fundamental drive. Atoms want to achieve a stable electron configuration, which usually means having a completely full outer shell, just like the noble gases in group 18, or group 0, as it's sometimes called. They are exceptionally stable and unreactive because their outer shells are full.
So other atoms react to try and get that full outer shell.
Yes, by forming ions. An ion is just an atom that has gained or lost electrons, giving it an overall positive or negative charge.
How does that help them get stable?
Take sodium again. 2, 8, 1. It's much easier energetically for it to lose that one lonely outer electron than to try and gain 7 more to fill the third shell.
Oh, so if it loses that one electron.
Its outer shell disappears, and the shell underneath, the second shell, which is already full with 8 electrons, becomes the new outer shell. Now it has a stable 2-8 configuration, just like neon, but because it lost one negative electron, it now has one more proton than electrons, giving it a +1 charge.
Yeah.
It becomes the sodium ion plus $.
And something like chlorine, 2, 8, 7, would do the opposite. It wants to gain one electron.
Exactly. It's easier to gain one to complete its outer shell, making it 2-8-8 like argon, than to lose 7. By gaining one negative electron, it forms the chloride ion. Textular. This electron transfer or sharing is the basis of all chemical bonding, and it all happens with those valence electrons in the outermost shell. #outro.
Wow. Okay, so we started wondering why things feel solid, and we end up seeing the atom is mostly empty space, defined by this tiny, dense nucleus Rutherford found. And understanding how those electrons are arranged in shells, well, that just unlocks the entire periodic table and why chemistry happens at all.
It really does, and what I find so compelling is the story of how we got here. It wasn't one single revelation. It was Dalton's solid sphere, then Thomson finding the electron and making the pudding model, then Rutherford's gold foil completely overturning that with undeniable surprising data. It shows how science works, constantly testing, refining, and sometimes completely changing ideas based on hard evidence. No idea is sacred if the facts contradict it.
A powerful reminder. So as you're thinking about all this, here's a final thought to chew on. We talked about atoms forming ions to get a full outer shell, striving for stability like the noble gases in group 0 or 18. Why are those elements, the noble gases themselves, so incredibly stable and unreactive? What is it about having exactly 8 outer electrons, or 2 for helium, that makes them just not want to react with anything at all? They're the chemical definition of content. Why?